before you begin this podcast, you should be fairly comfortable in your understanding of the difference between strong acids and weak acids, strong bases and weak bases. If you need to, go back and look at the first podcast in this series, which is more of an introduction. In this discussion, we're going to focus on the calculational process that you use with weak acids and bases. Okay, the thing to remember is that the weak acids and bases set up equilibriums. And so we're going to use our ice diagrams to solve for the equilibrium conditions. pH, the hydrogen ion concentration that we use to calculate pH, is an equilibrium value. Okay, so we need to do our ice diagrams so that we can find what our equilibrium concentrations are and use those to find the pH. So this is just an outline of the basic procedure. I'm going to pause it in a couple of places, but mainly this is just to kind of outline for you the main procedure that I'll be following when I work these problems. But essentially, we're setting up an ice diagram with either the dissociation of a weak acid or the dissociation of a weak base. Now, the nice thing about these is that the K values for the weak acids and weak bases are typically 10 to the minus 4 or smaller. And so many times we can use the approximation that the change in the initial concentration is negligible, and that way avoid having to do a lot of quadratics in the solution process. Okay, so let's look at an example here. Here we have the pH of 0.15 molar solution of acetic acid. So I know I'm going to need my K value. So my Ka for acetic acid is, let's see, 1.8 times 10 to the minus 5. All right, and if I write my equation, I have so my K value then is going to be equal to set up our initial concentration is 0.15. We don't care about the water. That's 0, that's 0. So minus x plus x plus x, and then 0.15 minus x, x, and x. So I'm going to make the assumption that this value is approximately 0 or negligible, and then plug in, and that's going to equal x squared over 0.15, which gives me an x equal to 164. Okay, and then just double checking. We want to see if our change is less than 5%. So 0.00164 over 0.15. And I get that that's approximately, so a little over 1%. So we meet the 5% rule, so we can use this X value, and this X that we solve for is our hydronium ion concentration. So my pH is the negative log of 0.00164, which is equal to 2.79. Okay, now here we have a base, and we want the pH for that. Okay, when we write our equation here, we have ammonia interacting with water, making ammonium ions and hydroxide. Okay. And we have 0.2100 minus x plus x plus x. Okay, my Kb, this is a base. Okay, we're producing hydroxide ions into the solution with its interaction with the water. So we're going to use a Kb value. And so that's going to be the NH4 plus OH minus over the NH3. And for ammonia, the Kb is 1.8 times 10 to the minus 5. Okay, and so that's going to be x squared over, we're going to use our approximation, 0.21. That gives me an x of 1.8 0.00194. Okay, and now remember here, my X is not my hydronium, but it's my hydroxide. So several ways I can use this. I'll just do my POH is going to be the negative log of 0.00194. And so that's going to be 2.71. And if I subtract that from 14, that gives me a pH of 11.29. Okay, if we have a mixture of acids, there are a couple of different situations that can occur. One is if one of the acids is a strong acid, then that's really going to dominate the pH. And so let's just take a look at this example where I have the nitric acid. I have so the pH due to the nitric acid then is going to be the negative log, so it'll be minus 0.114. Okay, and then if I have from the acetic acid, so that contribution then is going to be so if I added them together then, let's see, we have 1.3 plus 0.052 And so the pH from that, where we take both of them into account, is going to give me, 1.3052 would give me a negative 0.116. So the difference is out there in the thousandths place. And so really, in this particular mixture, there just isn't a significant contribution due to the weak acetic acid. So we would typically just calculate that based on the nitric acid. Now, if we have, here is a mixture of two acids here, both of them are weak, all right? So when that happens, what we want to do is we want to look at their dissociation constants. So the Ka for HCN is, hydrocyanic acid is 6.2, 10 to the minus 10th, and the Ka for the nitrous, I think, is much higher. Let's see, nitrous is 4.0 times 10 to the minus 4. So again, here we have a huge difference in the Kas, and so the nitrous acid is going to dominate the pH. So let's answer the first question. Here we have our and let's see, the nitrous is 5. So here I have 4 times 10 to the minus 4 is going to equal x squared over 5, and x of 0.0447, and let's just check that. So divide by 5, and that's like less than 1%, so we're good with that. That is my hydronium concentration, and so the pH then is going to be 1.35. Okay, now to answer the second question, what is the cyanide concentration at equilibrium? Okay, so here we are looking at the dissociation of the hydrocyanic acid and so we have, it's 1 molar here and no cyanide to begin with, but because we have another acid present, we have to consider the fact that there is a common ion. The hydronium ion is a common ion, and so we need to take into account the fact that the contribution from the nitrous acid is going to shift it left, right? Common ion. It's going to reduce the dissociation of the hydrocyanic acid, so we have to put that in as part of our initial. So 0.0447 would go here, and so we have minus x plus x plus x, 1 minus x, and x. And so again, we can use our simplification here. All right, so we have 6.2 times 10 to the minus 10 is going to equal, and we're going to say not only is this x going to be approximately 0, but that change in the x is going to be negligible as well. So we end up with 0.0447x over 1. And so 6.2, 10 to the minus 10th, divided by 0.047. And we get that the cyanide concentration is going to be 1.39 times 10 to the minus 8. Okay, pH of polyprotic acids. Again, as we talked about before, each of the protons coming off of the acid has its own dissociation constant. And typically, the dissociation constants decrease as we remove additional protons. So here, in looking at, say, the pH of 2 molar H2SO4, the first hydrogen is a strong hydrogen, and so there's complete dissociation of that hydrogen on there. That's why we consider sulfuric acid to be one of our strong acids. The second hydrogen is not significant relative to that. So in looking at the pH of 2 molar H2SO4, we would just look at one of those hydrogens, and it would be almost like we would have a mixture of a strong acid and a weak acid, and so we are only going to consider that the strong part. And so here we have the negative log of 2 for the first hydrogen coming off, and so we're going to get a pH of negative 0.3. Okay, so now let's look at what happens when we have a lower concentration of the sulfuric acid. When we have these lower concentrations, the contribution of the second hydrogen may actually be significant. Now we're going to look at what happens if the concentration of the sulfuric acid is more dilute. In that case, that second hydrogen may be significant. So if we again look, we have the strong hydrogen. So the pH due to the strong hydrogen is going to be the negative log of 0.001. And we're just going to do this as a point of comparison. So the pH, it would be a pH of 3 due to that first hydrogen. So then let's look at what would we get if we do take into account the second hydrogen. And so that one's going to be 0.001. All right, now we have to take into account the fact that the dissociation of the first hydrogen will affect this equilibrium, so we're going to include that. Okay, if we were to try to make our approximation here and say that x is approximately 0 and this x is approximately 0, okay, if we look at that, let's see, the Ka for the second hydrogen was 1 times 10 to the minus 2. What are we going to get? Well, we're going to get 0.01 times x divided by 0.001, which means we get an x of 1.2 times 10 to the minus 2, which is larger than our initial concentration, which of course makes no sense. So that right there tells us we cannot do that, and we've got to do the quadratic. So if you solve the quadratic for this, you're going to get the value of x as 4.5 times 10 to the minus 3. Okay, so then we're going to plug that in, and we get a hydrogen ion concentration there of 0.001 plus 4.5 5 times 10 to the minus 3, which is 0.0145. And if we take the negative log of that, we get, let's see, log 1.84. And so in this case, that second hydrogen actually is significant. So just be aware that if you're dealing with dilute solutions, that you may need to take into account that second or third hydrogen, even depending on which acid you're dealing with. Okay, the last topic we have is percent dissociation. And essentially, percent dissociation, or sometimes they refer to it as percent ionization, is just the amount that's dissociated divided by the initial concentration times 100. Okay, and again, this is why we were seeing the result we did for that second hydrogen in the sulfuric acid is this right here. The weak, or the more dilute the acid, the greater the percent dissociation. Okay, so let's look at 1 molar acetic acid. So 1 and 0, 0. The Ka, it's the Ka for that, 1.8 times 10 to the minus 5. It's going to be, we're going to do our approximation, which should work with this concentration. It's whatever 1. So my X is going to be 0.00424, and so my percent dissociation is just going to be my change, my X, divided by the initial, which is 1, times 100, and so I get 0.424%. Okay, so essentially, when we do our approximation and check our 5% rule, that's what we're checking. We're making sure that the percent dissociation is less than 5%. Okay? Alright, so here we're given the percent dissociation and we want to know what Ka is. So let's look at this. Here we have so this is our equation here. So if we were to write this out, let's just go our normal way here. Alright, so what do we know then about this? Okay, we know that, pretty much, we know that X over my initial times 100, that's percent dissociation. We know that's equal to 3.7. Okay, so X over 0.1 times 100 is equal to 3.7. And so that gives me, let's see, 3.7 divided by 100 and times 0.1. So I'm getting an X of 0.0037. Okay, so I'm going to plug that back up in here. And then 0.1 minus is 0.0963. And then to find my Ka, I get 0.0037 squared divided by 0.0963. That's going to be 1.42 times 10 to the minus 4.